Good morning. Am I audible to you guys? Okay, yes. So today we will start P plus tree deletion. Yesterday it was just half done. So we will just complete the delete portion today. Okay, let me share the screen first. Okay, so for deletion we have three different cases. We will just see them one by one. So this is the tree where I'll show the operations. So what are the main things we need to remember for deletion process? One is the order. This is a bakery with order 3. So the max children it can have is 3 and minimum children it's 1. Then the node should have minimum of m by 2 children, sorry, it's 2. It's m by 2. So max key m minus 1 is 2 and min key is 1. Okay, min key is ceiling of m by 2 minus 1. Okay, so these are the things you need to remember when you want to delete anything from a B tree. Okay, so first we will see the case 1. Case 1 is what? Case 1, just that we want to delete any key from the leaf. Okay, so in this case there are two subcases. One is that deletion of key does not violate the property of minimum number of keys a node should have. Okay, so one is violate number of keys and other is does not violate. Min key limit. Okay, so these are the two things. So first in this tree I want to delete 32. Okay, so first thing in this case I want to delete 32. So if I want to delete 32, first you need to search for the key. So obviously you will start from root node, then 32 is greater than 20, so it will be left of 20, and at the same time it is less than 40, so again it will be the left of 40, and for 20 it's right of 20. So in this way same thing will be here and 32 is here. Okay, so 32 is in leaf. So if I delete 32, is it violating the minimum number of key? Minimum number of key is 1, correct? So if I delete this 32, it's not going to hamper our tree. Okay, it will be still intact. So what I can do, I can directly delete this 32, and if I delete the 32 it's not going to hamper our minimum number of key things. Okay. Now in this tree we have only 31 left for this node. Now see, suppose I want to delete 31 now. Okay, delete 31. Now see, if I want to delete 31, isn't it violating the minimum number of tree? So in this condition, because minimum children is 2, but minimum key is 1, if I directly delete 31, it's going to violate the rule. So the condition is, first we need to visit the immediate left sibling. Then if the left sibling node has more than a minimum number of key, then we can just borrow a key from this node. Okay. Else if the immediate left node does not have like more keys, then we can just borrow from the immediate right sibling. Hope out. Okay. Mm, okay, so I want to delete 31. Okay. In this case, we have to just check the left sibling. What is the left sibling for 31? It's 25 and 28. Okay, in this node we have two keys. That means what? I can borrow a key from the left sibling because it has two. That means it can just give it the one more key. So but the thing is, we cannot directly take means 28 from here. If I directly do this, it's again going to be a problem. If I want to delete 31, suppose in this case 31 is not here. Okay, 32 we have already deleted. If I want to delete 31, so what's the process? First I'll just exchange the value to the parent, then I will get down the value of parent to this node. Okay, so it's just going to be an interchange. Okay, I'll just take the value from here and put it here. So in this way I am directly going to change it. What will be the value? So this 28, I'm going to just move it. Okay, so this 28 I have taken it here, and this there was 30 here, and I'll bring the 30 down there. So this is the process when we want to delete any node from the leaf, but if we remove the key, it's going to violate the minimum number of key portion. Okay, now again see, there's another condition. Now I want to delete 30. Okay, I want to delete 30 now. Now you see, if I want to delete 30, what's happening here? What's the rule? If you want to delete node from leaf, I can take either from the left or right. So obviously first I'll check with left. Okay, I want to delete 30. If I check the left sibling, I can see there's only one key there. Okay, that means what? I cannot borrow the key from the left side because minimum number of key is 1 and it contains only one key. So I cannot borrow it from here. So what I'll do? I'll check the right sibling. Again, the right sibling has only one key, which is 35. Okay, that means what? Again, I cannot borrow the key from the right sibling, correct? Because both left and right sibling has just one key, and which is the minimum number of key. So in this case, what's the process? We need to just merge it through the parents. Okay, we are going to merge through the parents. So what will happen if I want to delete 30? So I'm going to just merge this along with 28. Means suppose this is your This is 28, this is 33, this is 25, 30, and this is 35. So if I want to delete this node, I am going to merge this. After merging, the key will be 25, 28 and 35. Okay. So after merging, the intermediate state will be like 25, 28 and 35. But again you see the maximum number of keys can be 2, right? And after merging we have like um, total 3 keys. So again you need to check with the parents. So in this case the only remaining parents will be your 33 because I have deleted merge this 25, 28 and 35, right? I just merge these values to delete this 30, right? So in this case your root is 33, and after combining this, merging these 3 values, 3 keys are there, and which is not possible. So what I am going to do, I am just going to split these keys again. So after splitting, left of 33 we will have 25 and 35, no sorry, 28. So we also need to maintain the BST rule, right? So 3 is there, only one node is there, so I'm going to just split it. Okay, after splitting it will be 25, 28, and here it will be 35. Okay, so this same thing I'll just incorporate here. Okay, after this intermediate step I'll just putting it here. So after this what will be the resultant? This one is gone, 33 is there, 25, 28 was there, and 35 will remain here. Okay, I'm just writing this step, this step, this step I'm putting it here. Is this clear? So what are the conditions when you want to delete anything from the leaf node? First you will check whether it violates the minimum key or not. If it does not violate the minimum key thing, you can directly delete the key. Okay, if it violates the minimum number of key thing, you can take a key from its left sibling. Okay, if your left sibling contains just the minimum amount of key, then you can borrow from the right sibling. Okay, that's the condition we did. So when you borrow a key from either left or right sibling, then what happens? We just exchange the parent value, correct? So third case, subcase is that if both left and right sibling contain just the minimum number of keys and it cannot give you one more key because it doesn't have. So in that case, what we do, we just combine the left sibling, right sibling and the parent. Okay, after doing that, again we split the value just to maintain the BST property with the parent one. Okay, so this is the case 1 when we want to delete anything from the leaf node. Okay, so now let's see if we want to delete any node from internal node. Okay, this is the case 1 we want to delete from leaf node. So I'm just, is this case clear everyone? Case 1, delete from leaf. Okay, let's say yes. Okay, so case 2 is, suppose if the key to be deleted lies in the internal node. Okay, so now we want to delete anything from the internet node. So I'll just skipping back the old tree. It was 2023. It is the main tree, okay? 31 and 32 and 35 was there. Okay, so we just went back to our normal key. So case 2, delete from internal nodes. Okay, delete from internal nodes. Now suppose I want to delete 33. Okay, now I want to delete this 33. Delete this one. Now what you need to check, we have to see which internal node to delete. Then that node will be replaced by an in order predecessor if the left child has more than a minimum number of key. Okay, the condition is same like your left thing. We can just go to the left child and check whether it has more than minimum number of key. And if yes, then we are just going to replace that value with the in order predecessor. Okay, so for 33, if I want to delete 33, what is the in order predecessor? Left editor. For 33, the left node is this one, and this one has 31 and 32. We are going to replace it with the in order predecessor. So left child. So 32 is your in order predecessor. So I'm just going to replace this value 32 and delete this 33. Okay. So after doing that, what will be the value? 32 will be here and this remains deleted. Okay. So the case 1, if we want to delete internal nodes, we can just replace with the in order predecessor if the left child has more than key. Then again, if not, means it does not contain the minimum number of keys, then what we can do, we can just replace by the in order successor of the right child. Okay, so suppose in this case, now I want to delete 30. Okay, I want to delete 30 now. If I want to delete 30, now I can just take from the left child, and which will be again the predecessor. So for 30, what is in the right? What is in the right? So for 30, if I delete 30, 32 is already there, correct? So we can directly delete this 30, but the thing is, this 31 is with 30, is the right child of your 30. So in this case, if I want to delete 30, what we need to do? We just combine, we will just combine the children of 30. Okay, because 32 is already there, so I can directly delete this 30. So what can do? I can just delete this 30 and I can just combine this 35 and 25 and 31. Okay, so if I combine, so 31 will come here, this node will be gone. Okay, So you can just replace this 32 here. It's fine. It's not going to hamper. Okay. So one node is gone. So in this case, what we saw, the internal node which is deleted can be replaced by an in-order successor if the right child has more than the minimum number. Okay. Now see, if either child has exactly a minimum number of keys, then we merge the left and right subkey. So that's what we just did, correct? Before we want to delete it, and if I want to take from the right side, we had only one key. Okay. So initial we had 30 and 32, 25, 31 and 35. So in this case, we can take the right from the right predecessor, but it contains one, and since it has only one, we cannot directly borrow it like the last time. We cannot replace the value, so we can just delete it and just merge both the children because both sibling had just one kid. Okay, so now let's see the case 3. Okay, that one is too congested. Case 3, suppose let's take a small. So okay, so in this case, suppose our height has already shrank like to a bit smaller now. So now just see, I want to delete 10. Okay, I just small it out a bit. So suppose I want to delete 10. Okay, delete 10. So what's the process to delete 10? I can check with the left and right predecessor, right? But for the both cases, it just contains one key. So what I'm going to do, I'm just going to merge these values. Okay. So if suppose it's just the intermediate step actually. So oh, class ko yun. Explanatory pa? Oh, Mark. Oh, class ko yun. Okay. So if I want to delete this node, so the remaining node you can just merge these two. So it will be 5 and 15. This will remain same, of course. 30 and 70. So after this, see, if I want to directly this, suppose this node is not there. Again, the next process is what? I can just combine these two values. Okay, if I want to combine these values, these two parent I am combining here. Okay, so this will remain same 5 and 15. This can remain here 30 and this one remains 70. Okay, So sometimes if I see in this previous case, when I deleted 31, 32 was there, correct? Since 30 was there, so I just directly combine this left and right sibling. So in the third case, I want to delete node from the internal key from internal node, but there's only one key. One key means what? It's violating the key. Wait a minute. Just wait. Okay, sorry for lots of disturbances. One of our colleague is going to get married, so he just came to invite. Anyways, so these are the three cases. Clear to everyone? So in the second cases, so we saw the three cases. First case, we want to delete something from the leaf node. Again, for the leaf node, there are two subcases. First, we check if it violates the minimum number of key or not. If it does, we can directly delete it. If not, then we have to again just borrow keys from left and right siblings. Okay. Then second case was we want to delete something from the internal nodes. If your internal node contains two keys, like in this way, two keys, even if I want to delete 30, it's fine because 32 is already there. Just that we are just going to combine the left and right sibling of that particular key. Okay. Then the third subcase means one of the case, but again it's the same thing. We are going to delete something from the internal node. Now in this case, there is only one key in the internal node, and if I directly delete it, what will happen? The minimum number of key that violates the rule. So in this case, suppose the node is not there, I'm just going to merge this left and right sibling of that particular key. Then there won't be any link, so I can just directly merge the value of parent and this node. Okay, because in this case also it has just 111. So I can just directly combine these values and keep it like this. So if there are some more keys, again we have to do some more processing. Okay, suppose something is here in this value, then we again have to merge it, then again split and then connect it. Okay, in the simplest case, if you want to delete something from the internal node and it contains just one, we can just merge the parent and the one of the internal node and we can create a new node. And this one is not violating the rule. So this is all about your B tree. So insertion deletion done. So I hope all of you clear. So apart from uh, B tree, so was the complexity for deletion for the best case for deletion, your best case is, of course, it will be just the height of your tree. Everything is set. So height of a tree is, of course, log n. Otherwise, for deletion, worst case is on. Sorry, space complexity. On is the space. Okay. Anyway, it's going to take all the time. Okay. So apart from B tree, there is one more variant which is B plus tree. Okay, The only difference between 2 मिनट के लिए इंसर्शन का समरी बता दीजिए. Okay, you want insertion. Insertion. Okay, insertion for confusion है बहुत. हाँ, थोड़ा confusion तो है. Insertion is actually very simple one. Insertion, what you will do, you just need to remember the maximum number of keys. See, if you are going to add something, you just need to check whether it is overflow condition or not. The moment you see a overflow condition, you are just going to split it. Okay, so okay, I just show one portion. First insertion, right? First we want to add 8. Okay, I'm going to just consider a three-way key again. So for three-way, there can be 3 children and key can be 2, right? So 8. Next I want to add one more item, maybe 9. So I'll just add 9 here. Now suppose I want to add 10. So if I want to add 10, it's a overflow condition because it's a three-way. So minimum number of key is 2, m minus 1. So if I want to add a new item here, what I'm going to do, I'm just going to find a median. Okay, find a median value and push it up there. It's a bottom up approach. So what I'll do, I'll put just 9 up, push up there and just make these values to the left and right. Okay, so in this case 8 is left of 9 and 10 is right of 9. So it's maintaining the value, correct? So suppose now you want to add one more item, which is 11. 11 is greater than 9. Of course, it will come to the right side. Now in the right node, just one key is available and maximum number of key is 2, right? So I can directly add key here, 11 here. Now suppose I want to add one more item and I want to add 15 now. Again 15 is greater than 9, so I'll put it in the 9 right side. So suppose I want to add 15 here. Again it's an overflow condition. The maximum number of key we can keep is what? 2. So again I'm going to split in the median. Median is 11. It will go up there. So your 9 will come here. See, if I push it up, this 11 will go up. The parent has just one key and the maximum number of key is 2. So I can just put 11 here. 8 will remain here. Okay. And 10 will come here and 15 will come here. 11 I pushed it up. So 10 will be just left of 11 and 15 will be right of 15. Okay. So now suppose I want to add more item, which is 20. Okay. Now 20 is greater than 9, then again greater than 11. Okay. So I have to put it in the right side. So in this right side there is only one key, which is 15. That means I can add 20 here. Right. 2 keys maximum. So now again suppose I want to add 17. Okay, I want to add 17. Again 17 is greater than 11. Okay, greater than 11, that means I will come to the right side. Now 17 is greater than 15 but less than 20. And if we follow the BST rule, so 17 should come here somewhere in the middle. So your intermediate node should be 15, 17 and 20, right? So we just imagine we have just added this 17 here. So what I'll do, again push up the median value up there, right? So 17 will go up, 17 will come here. Suppose Just imagine 17 is added here, and after adding 17, this node will have 9, 11 and 17, and this will be splitted. 15 will come here, 20 will come here, correct? This is just 17. I pushed the 17 up. There is one more, so I just added 7. This is just intermediate, and this will remain same, 11, 10, and this is 8. Okay, it's different node. Okay, so now again same thing in this node. It's violating the rule, maximum number of keys 2. So again I'll find the median and push it up. So 11 will go up. Okay, then 9 will come down, 17. So rest will remain just same. Okay, 18 will be there, 8 will be there, 10 is there, 15 and 20. Okay, इस बीच वाले को भगा देना है. हाँ, 3 जब भी की से मैक्सिमम से ऊपर हो गया, मीडियन वैल्यू, मीडियन मीन्स मिड वैल्यू को बस ऊपर उठा दो. तो बीच वाला अगर ऊपर उठा दिया तो जो लेफ्ट में है लेफ्ट चाइल्ड बन गया, और राइट चाइल्ड जो है वो राइट में रह गया. सिंपल. इंसर्शन इज मच इजियर. सिर्फ मैक्सिमम वैल्यू जब भी मैक्स हो जाएगा, मतलब मिनिमम वैल्यू से ज्यादा हो जाएगा, मिनिमम नहीं सॉरी मैक्सिमम की से ज्यादा हो जाएगा, यू जस्ट नीड टू फाइंड द मिड वैल्यू, देन पुश इट अप and make left and right. That's all. Okay, this thing I just B. Next is the B plus tree. Then hoga 18. So there is one more tree which is B tree. So only difference between B and B plus tree is that all the internal nodes, the leaf nodes, are connected to each other just like your linked list. Okay, so your B plus tree, this is your B tree. If I say B plus tree, that means what? All the internal leaf nodes will be connected to each other through a link. Okay, it's more like a linked list. If it's a B tree, there won't be any connection between the leaf nodes. And if it is a B plus tree, that means all leaf node will be connected through a link, and it will form like a linked listing. Okay, that's the difference. So what are the other property of B plus tree? It's just extension of B tree, and it allows efficient insertion, deletion, search. Anyway, so in B tree, keys and records, see, mainly B and B plus tree are used for what? Disk accessing, right? We use B and B plus tree when we don't store anything in main memories. Our main memory has a specific limit, right? Whenever and if you want to store anything in main memory, we can use any data structure. But sometimes when we have lots of data, we cannot just store things in main memory. In that case, we use a secondary memory. Secondary memory means mainly disk and all. But the thing is, processing means accessing any data from the disk takes time, right? It will just copy paste the thing, then it will process. So this accessing time is much higher. To minimize the disk access time, they develop B and B plus tree. Okay, so B and B plus tree is mainly used when we save some things in secondary memory. So in B tree, keys and records both can be stored in the internal as well as leaf node. But in B plus tree, all the records or the data only stored in the leaf nodes, and internal nodes can only store the key values. Okay, so leaf nodes of B tree are linked together. Same, the B tree used to store large amount of data and all. So what's the difference between B plus and B tree and B plus tree? Already mentioned, search keys can not be stored repeatedly. All records will be in leaf nodes in case of B tree. And in case of B3, you can just keep any record in B3. Remember in the disk accessing, I just mentioned we have sectors, then we have indexes. I already explained the thing about multi-level indexing. Multi-level indexing. So this is all about multi-level indexing using both B and B plus tree. So what is the advantage of B plus tree? We can just access and fetch all the records in equal number of time. Then height of the tree will remain balanced and a bit less compared to B3. Okay. Then we can also like access the data stored in B plus tree sequentially, because all the records will be at the leaf node, and the leaf node is more like a um, linked list. Okay. In B3 we just keep all the things in a both leaf node and the internal node, and in B plus tree we are keeping all the record just in the leaf nodes, and these leaf nodes will be stored in your disk. And these things you can see here, this is nothing but actually just indexes. Okay, these are nothing but just indexes. So for insertion of B3, we can just insert a new node as leaf node. Okay, and so on. Maybe I can just show you one example. Lecture time, it's going to end in 5 minutes. Okay, next class I'll just start with this insertion deletion. It's almost same, just that I'm telling you all the records are stored in the leaf and these are just your indexes. Okay, it's going to end. So I can just give you a quick review in the next class, but next class we will mainly start with the graph. Okay, that's the last chapter, graph and all the sorting algorithms in the last unit. So on Thursday I'll start that, then again in lab class we will start with the sorting algorithms. Okay, that's all for today. I hope you are clear about insertion and deletion of B3. Okay, just that process is same. The same way we insert things in B3, just that when we push up, okay, I just give a normal thing. Okay, I'm just giving an example in this case. Okay, quick example. See, okay, the quick thing was 8, 9, and 10, right? Okay. 8 sorry, 8 and 9 was there, then I wanted to add 10, correct? 10 is the limit because maximum number of keys can be added 2. So what we did, we always find the median value and push it up, correct? So we will do the same thing, we'll put 9 up there, but the only difference here is that we will also keep the same value down here as well. Okay, now it's up to you where you want to keep the copied value. You can keep either in the left side or you can also keep in the right side, and it's completely up to you. Okay, you can make it a right biased or you can make it a left biased. So same thing, you are going to find a median and push it up there. In normal B3, we just split the values into left and right. We do the same, but at the same time, the median value which we push up, that will also remain in the same level because we keep all the main records in the list. Okay, and previously in B tree we keep all the things in internal nodes and the leaf nodes, but in this case B plus tree we keep all the records in only leaf only. So whenever we push the medium up, we keep the same value. That 9 value will also remain in the leaf side. Then it's completely up to you where you want to keep it. You can either keep it in the left side or right side. Normally if it is a BST, your right child should be less than equal to parent, correct? So it's better always keep that value to the right side, because it's also a BST. For the BST, the left children should be less than the parent and the right children should be greater than equal to the parent. So the same thing will come here. Okay, is this clear? That's the only concept. The rest is just same, but if it is a leaf, then only add this connection in the end. Okay, is it clear? So in this case also, if I want to keep 17, I push up there, right? So 15 I wanted to add here. So once I push 15 up there, I'll also keep 15 here. So that's the only difference. Okay, just stop sharing and take your attendance. Yes. Okay, done. Your attendance done. I'm just ending the meeting now. Thank you.